All right, everybody. So I am stubbing for Miss Williams here on this video. So this is 3.8. We're going to talk about implicit differentiation. And what's going to happen in this section is we're going to look at not just functions, but some equations where either the y is not isolated or it's impossible to do so. All right. So we're going to take a look at equations. Some are functions and then some are not. But this is what this technique will allow us to do. Now, up until this point, whatever we've been finding the derivative of, the function has been defined what's called explicitly. It's a function y. So y is a function of x. That's what I meant to say. All right. For example, you see this function right here, y equals uh, x squared plus 1. Okay. That function is defined explicitly. So y is defined explicitly as a function of x. Okay. Whereas if you take a look a little bit later, you see this y minus x squared equals 1. This is defined what's called implicitly because the y is not isolated. Okay, so it's all mixed up. So we're going to look at functions and equations where, again, this is the technique that we don't necessarily have to solve for y, and then um, especially for ones where we can't. There's going to be ones where we just cannot solve for y at all. All right. Those are going to be the ones we use this technique that's called implicit differentiation. So it's going to allow us to take the derivative without having to have y isolated, and then just some function of x on the other side. Okay. So if you're to look in the textbook, this is starting on page 309 right here. All right. You could see that if we had to do, so y equals the square root of 25 minus x squared, well, that's got two different pieces to it. All right. Because if you look at the graph, you've got this semicircle here, and also we lose if we rearrange this and look at the equation of the circle where this comes from x squared plus y squared equals 25. If you took a look at this and you tried to solve for y, you would get y equals the square root of 25 minus x squared. But you would have to consider the positive and the negative. Okay. If you just consider the positive, that's a function. But if you consider both sides, I mean, you could consider it a piecewise defined function, of course. All right. But on its own, it's not a function. All right. So x squared plus y squared equals 25 is not actually a function. It's an equation that's defined implicitly because y is not isolated. Okay. So we're going to take a look at ones, like I said, where we're going to look at where either we may not necessarily want to solve for y, just keep it where it is, or we just can't. All right. And that's going to be our goal here. So if you look, I just want to make sure I keep track of where I am here. All right. So this is probably the most important part, the box on page 311. And it has the strategy on how to do these implicitly. All right. And when you do these implicitly, this is where the chain rule comes into play. All right. Because think about this. Think about y, remember, is supposed to be a function of x. So when you take the derivative of y, you have to consider that y is the outermost function, and then there's a function of x within it. Okay. So here's how it goes. So it says take the derivative of both sides of the equation. And of course, here's what I was saying. Keep in mind that y is a function of x. All right. So basically, here's what this part's saying right here, where it says d dx sine of x equals cosine of x. That's just taking the derivative explicitly, so you don't have anything weird going on there. But when you take the derivative sine of y, remember y itself is a function of x. So you take the derivative of sine first, which is why you get the cosine of y. But then you have to take the derivative of y. Now we don't know what it is because it's an implicit definition here. All right, so the best we could say is the derivative of y is dy dx. So we differentiate y with respect to x. So that's going to be the term we use anytime we use the chain rule for y. Okay. So keep in mind, anytime we take a derivative of y, we must multiply by this dy dx because it's the end of the chain rule. Okay. All right. So then what you want to do, and a matter of fact, here it really doesn't matter. But what you want to do is you want to get all the terms that have dy dx on one side of the equation, and then the non-dy dx terms on the other side. They recommend from the textbook that you get dy dx on the left and then non-dy dx on the right. And that's usually what you do, but again, it doesn't matter. as long as you get dy dx to one side, non-dy dx terms to the other. And the reason you want to get dy dx on one side is so that it's a common factor. You factor it out, and then you solve for dy dx by dividing by basically whatever you factor the dy dx out of, you'll multiply it by an expression. You then divide by the expression on both sides. Excuse me. It's pleasant to hear me sneeze on that. Sure. Okay. All right. So that's going to be our process here. Okay. So now let me go ahead and walk you through some examples. Let me see the one she has written out for me that she wanted me to do. I'll go ahead and just put these. I'm going to go ahead and go to the whiteboard. I'll just write them out for you guys. All right. So let me get a new share here. All right. So I'm going to or let me go ahead and here's the, sorry. Give me a second here. Okay, I think I'm ready to go here. All right, so I'm going to go ahead and differentiate this expression here. So I've got 6x squared plus 3y squared, and we're going to set that equal to 12. Okay. All right. So we can try to solve for y, but again, to make it a complete function, we'd have this piecewise that we saw in that example with the circle I had. Remember the x squared plus y squared equals 25? Same idea here. All right. So a much easier way to go will be to do this implicitly. So what we do is let's go term by term. And so we'll start off with, we're going to take the derivative of each side. So I'm going to have d dx of 6x squared plus 3y squared. And then I take the derivative of this side as well. So d dx 12. Okay. Now, when you take the derivative of, this is what I was kind of saying right here, when you have multiple terms like this, you take the derivative of each term separately. So you would do d dx 6x squared, put a parenthesis here on that, plus d dx, take the derivative of 3y squared, and then we're going to take the derivative of 12. Okay. All right. So let's differentiate each term with respect to x. So 6x squared, that's going to be a power rule. That should come out to 12x. Okay. Plus, and then the 3y squared, remember, this is going to be a chain rule. So we start with the 3y squared. All right. Again, you would use your power rule for that. That's going to come out to 6y. But then you have to go, all right, I got to multiply by the derivative of y, which the best we can say is dy dx. So derivative of y with respect to x. Okay. And then we set it equal to the derivative of 12, that's a constant, is just 0. Okay. All right. So then from here, I want to solve for dy dx because that will explain what is the derivative. So it's the derivative of y with respect to x. Okay. So let's go ahead and do that. So remember, I want to keep dy dx on one side of the equation, and then anything without dy dx I want to send to the other side. So I'm going to get rid of this 12x by subtracting it. And I'm going to need a new page here in a second. So I'm going to have 6y dy dx equals, and remember what I had here, I have negative 12x on the right side. Okay. And then my last step is now I would remember in that list of steps we had factoring out a dy dx, but I only have one term, which is good. So now to get dy dx isolated, I divide by 6y. Okay. So that gets me dy dx equals, so negative 12x divided by 6y. I'm going to simplify that down to, I believe that simplifies to negative 2x over y. And that's your answer. And your answer can have y, remember, because y is a function of x. Okay. Or y is an expression of x. So this allows us to take the derivative. Like I said, it takes derivatives now of any curves, even if they're not functions. Okay. So that's our first one. All right, let's do another example. I'm going to do a few for you. I want to say right quick, but these are not quick at all. All right, let's take a look at some of the here. The next one I want to do is, let's try, for example, let's try 3x to the third plus 9xy squared equals 5x to the third. Okay. All right. So we take the derivative of both sides, right? But what's going to happen is, because we have these terms, I'm going to take the derivative of each term. Okay. So I'm going to do d dx of 3x to the third. We'll take the derivative of that. Then we'll take the derivative of 9xy squared. And then we take the derivative of 5x to the third. Okay. Oops, let me make that. I'm going to make that a little bit nicer. Hold on. Here we go. Okay. So we'll go term by term here. So this first one here, 3x to the third, the derivative, again, just a simple power rule, is going to be 9x squared. Okay. So now when you look at this second term where you got 9xy squared, all right, remember, technically you have two different functions. Remember, y is supposed to be a function of x, or an expression of x. So we have two different functions of x being multiplied, all right? So because of that, I need to use product rule. So I'm going to call 9x like my first piece, my first function, and then y squared is going to be the second. So here's how it's going to go. I'm going to do first times the derivative of the second, and the derivative of y squared is 2y, times, I just did a derivative of y, I've got to multiply by dy dx. So that's half the product rule. Then I do plus I rewrite the second, and then we do the derivative of 9x, which is going to be 9, okay? So any term, when you're doing implicit differentiation that has x and y in it, you have to use a product rule, okay? And then we set this one equal to, now what's the derivative of 5x to the third? That one should be 50, I'm sorry, did I say 5? Yeah, I did. I can't remember if I said 5y. 5x to the third, that's important. Okay, the derivative of 5x to the third is 15x squared, sorry. If it were y, I'd have extra stuff on it, right? Okay. So let me go ahead, let's kind of simplify, make it a little bit easier for ourselves going forward. So I've got 9x squared plus, oops, sorry. The point is I wanted to simplify there. All right, so 9x times 2y, I'm going to call that 18xy dy dx. And then this is going to be plus 9y squared equals 15x squared. Okay. All right. So now I want to, and again, I've got one term with dy dx, so that's good. So I want to isolate that term on one side, and anything that does not have a dy dx is going to go the other way. So I'm going to get rid of minus 9x squared and minus 9y squared. Okay. So we'll subtract it here. I'm going to do minus 9x squared. Okay. All right. And just give me a second, folks. I'm just double checking to see I got everything right here. Yep. Let's make sure my math is sharp. All right, so now we've got the 18xy dy dx. That is isolated on one side. And we set that equal to all the terms moved over. Now, if we look, we could actually combine. We had 15x squared. We can subtract 9x squared to give us 6x squared. And then remember the other term we have here, we have minus 9y squared. Okay. Now our goal here, let's completely isolate the dy dx. To do that, we're going to divide by 18xy. And therefore dy dx equals, so since it's a single term, I'm going to divide each term on the other side by that 18xy. So I'm going to split it up like this. So 6x squared over 18xy minus 9y squared over 18xy. And then if you just simplify each fraction, I believe this comes out to x over 3y, this first one. And then the second fraction will come out to y over 2x. And that is as far as you need to go there. That is your derivative. Again, it can have y in it. Remember, y is a function of x, okay? All right. Hope everybody feeling good so far. Those are just first couple of examples there. Okay. I'm just going to pause this right quick. I just got to make sure everything is in order here. All right, folks, sorry for the little delay. I was just making sure. My notes I thought were, I was making sure they were in order. I thought they were shuffled, but they were good. So let's keep going here. So we're doing implicit differentiation. I want to do another example with you folks. Actually, I'm going to do quite several, but so this next one, again, we're going to find the derivative of y times the square root of x plus 4. And we set that equal to xy plus 8. Okay, now, let's be a fun one, especially on the left side right here. So when we do the derivative, it's going to be, of course, we're going to take the derivative with respect to x of this expression y times the square root of x plus 4. And then we set that equal to the derivative with respect to x here of xy plus 8. Okay. All right. So again, what we have on the left side of this equation is we've got two different functions of x being multiplied. You've got y, and then you've got the square root of x plus 4. Okay? All right. So I'll go through, and it's going to be a product rule, and then we'll actually have some other chain rule going on. Excuse me, voice just cracked. Some other chain rule going on as well. All right? Okay. So here we go. It's going to be the first, which is y, times the derivative of the square root of x plus 4. And for that, you're going to use a chain rule because you have an expression being raised to a power. So you start with that square root. And keep in mind, it's going to be 1/2. So the 1/2 comes in front, times x plus 4 raised to now the negative 1/2. And then just for emphasis, I'm going to put times. Then you do the derivative of x plus 4 to get 1. Okay? All right, remember, that's only half the product rule. Then you rewrite the second, which is the square root of x plus 4, times the derivative of y, which is 1, and again, I'll emphasize the 1, times dy dx. Okay? All right, now I'm going to struggle to squeeze this on one line here. So on the right side, we've got xy, and then we're going to take the derivative of 8. So remember, xy, that's another product rule. It's going to be first times the derivative. So x times the derivative of y, which is 1, times dy dx. So we did a derivative of y. Plus, and then it's going to be the second, which is your y times the derivative of x, which is just 1. So your product rule is done on the xy term. And then now we do plus the derivative of 8, which is 0. Okay? All right. I'm going to go ahead and clean this one up a bit here. Okay? So for this first term right here, okay, I'm going to write it a little bit nicer here. I'm going to keep the y on top. And then I'm going to have 2, and then that x plus 4, the negative 1/2, will drop to the denominator, and it becomes the square root of x plus 4, like so. Okay. And then the second term, I've got square root of x plus 4 times dy dx. Okay. Equals, then on the right side, I've got x times 1 times dy, that's going to be x dy dx. Plus y, and then of course the 0 just disappears. Okay. All right. So now I've got multiple terms of dy dx, and they're on both sides of the equation. Okay. It's really your call which way you want to move these. All right. Um, I'm just going to show you as an option. All right. I'm going to move the dy dx's actually to the right side of the equation, and the non-dy dx's to the left. Okay. Remember, you don't have to do that. I'm going to subtract. So I'm going to subtract this x plus 4 dy dx. That's supposed to be a 4 there. Hold on. Let me make that look a little bit nicer. Okay. 4. Okay. X plus 4 underneath the square root dy dx. And then I'm also going to, I want to get the y term that does not have a dy dx. I'm going to move it over to this side. Okay. Again, you don't have to do it that way. All right. You could have subtracted x dy dx and then subtracted this whole term the other way. It does not matter. Okay. So here's what I've got. On the left side, I'm going to have, let's see, make sure I got this, keeping track of everything, y over 2 square root of x plus 4. And now I've got the minus y. And then we set that equal to x dy dx minus the square root of x plus 4 dy dx. Okay. All right. Now, again, the reason for the first time in the examples that I've done, I'm going to have to do this next step because I have multiple terms with dy dx. But the reason you move them all to one side of the equation is that now it's a common factor, and you factor it out. So I'm going to have dy dx, and then in parentheses, what's left when you take that dy dx out of both terms? So you're going to have x minus the square root of x plus 4. Okay? And now the reason for that, of course, is now to isolate the dy dx, I would divide by this entire factor. Okay? So I'm going to divide by that whole thing now. Okay? Which now leads me to my answer, and this one looks terrible, but it's how it is sometimes. So my answer is going to be y over 2 square root of x plus 4 minus y all over x minus the square root of x plus 4 equals dy dx. And that, folks, is our answer. Okay? They don't always look nice with this implicit stuff, but it's still, again, for some, especially in this one, we can't isolate the y. Okay? Or maybe we could, but it becomes even messier to do it explicitly. All right? All right. Keep the party going here. Oh, this one's going to be fun. This next one. All right. Here we go. Let's go. How about y sine of xy equals y squared plus 2. This one you definitely have to do explicitly. Again, just like the last one. There's really no way to isolate this y. Okay. So we're going to do the derivative of both sides of the equation. So again, we'll do d dx of y sine of xy. Okay. Equals, and then we'll do d dx y squared plus 2. Okay. Let me just, sorry. Okay, here we go. Just making sure yeah. I got to keep an eye on technology, make sure it's working properly. Sorry. Okay, here we go. So now on this left side of the equation, you have y times sine of xy. So you've got, again, you got two different functions being multiplied. So you have to use product rule. So let's consider y as our first piece, sine of xy as our second piece. So it's going to be the first times the derivative of sine of xy. Okay. Let's see how she's, okay, I got this. So the derivative of sine of xy and this is going to be this is going to be a mess right here. Watch what happens here. So sine of xy, you're going to do chain rule. So sine is my outermost function. I got to do derivative of sine, which is cosine, times, now you go inside to the xy and you do the derivative of that, which in itself is going to be a product rule. Okay? So you're going to do first x times the derivative of y, which is going to be 1 times dy dx. Let's put the dy dx here. Plus the second times the derivative of x, which is going to be 1. Okay? Now, if you can believe it, we're only halfway done with the overall product rule. That product rule here was just for the xy. Remember, we've got a big product rule going on for this entire thing. So we're only halfway through. Remember, this was first, d second. Okay. Oops. Sorry. And then we're going to have plus the second, which is sine of xy, times the derivative of y, which is 1, but we've got to multiply by dy dx. Okay. Whew, yeah. Take a deep breath there. All right. Now on the right side, we're going to take the derivative of y squared, and that's going to be 2y times dy dx. So that's the derivative of y. And then the derivative of 2, finally we got something easy for us, is just 0. It's barely able to squeeze it in. Okay? All right. So, let's see. So I'll try to make sure I got everything straight here in the notes. Make sure everything's lined up. All right. So let's simplify this left side as much as we can before we work any further. So I'm going to take this y cosine xy. Let's distribute to each term on the inside of this parenthesis. So it looks like to me, I'm going to get xy, or yx, doesn't matter. I like like alphabetical order. So it's xy cosine of xy times dy dx. Okay. Then we distribute to the y, and we're going to get plus y squared cosine of xy. And then we have plus sine of xy dy dx. Sorry, that's supposed to be a dy dx. And we set that equal to 2y dy dx. All right. Awesome. Awesome. We're in a good spot here, I think. Okay. All right. Like I said, just making sure I got everything here. All right. So now we got a lot of dy dx terms. I want to isolate on one side. I think the easiest way, because most of the dy dx terms are already on the left. I'm going to get all the dy dx stuff to the left. So let's subtract the 2y dy dx. Put it over there. Ah, geez. Sorry. I made a mess of that one. Let me just try that again. Right? And then we have this one term without the dy dx, this y squared cosine xy, that has to go the other way. So we'll put it over here. Okay? All right. Let's see if I can straighten everything out here. So we've got the xy cosine xy. Y squared cosine x y dy dx. Okay. Oops. Sorry. Erase all that. Ignore what I just said. I got my terms mixed up here. xy cosine xy dy dx. It's really easy to do. That's why I had to keep looking at my notes, make sure I got everything straight here. So that's xy cosine xy, sorry. And then I've got the sine xy dy dx. And then I've got that minus 2y dy dx. And we set that equal to whatever we sent to the right side, which was the one I mistaken before. So it's minus y squared cosine xy. Okay, so we did all that, got everything organized, and now everything on the left side has this common factor of dy dx. So we pull that out, and that's going to give me left xy cosine xy plus sine of xy minus 2y, and we set that equal to negative y squared cosine xy. Okay, all right, I'm going to save myself a little writing here. But you can see the last step here is we want to isolate the dy dx. So we're going to divide by this whole factor here. Okay, so the way your answer reads, again, not the nicest looking answer in the world. So it's negative y squared cosine xy. And we put that all over this entire factor. So we put xy cosine xy plus sine of xy minus 2y. And there you go. So you can see these do get a little messy, but they're necessary. But hopefully you saw, again, where chain rules and product rules come into play. Just be aware of that when you're doing these. Okay? It's really easy to miss, especially when you see the y. Remember, y is a function of x. So keep that in mind as you do these. Okay? All right. Another quick pause, and I will be back to do the next problem. All right, so I'd like to do a couple coming up here where not only are we going to find the derivative, but we got to find the equation of the tangent line. Okay? All right. So this is going to require not only the expression, but also we need a point on the graph somewhere. All right. So let's take a look at, this is number 311 in exercises section 3.8. So it says x squared plus y squared plus 5xy equals 14. And we're going to find the equation of the tangent line at the point 2, 1. Okay. All right. Oh, excuse me. So let me go to the whiteboard. We'll get some work done there. All right. So I got the problem written. So here's our expression at the point 2, 1. That's our curve. So we do the derivative. X squared y squared is going to require a product rule. Okay. So x squared is going to, we'll take the, so I'm going to leave that first one alone, x squared, and then derivative of y squared is going to be 2y times dy dx plus, and then it's second times derivative of the first, which is going to be 2x. Okay. Then we go 5xy, that's another product rule. So I would consider 5x my first function, y is my second. So it's going to be first times d second. Derivative of y is 1, but then that's, you got to multiply that by dy dx. And then it's plus the second times the derivative of 5x, which is 5. And we set that all equal to, what's the derivative of 14? 0. Okay. All right. Make this look a little bit nicer here. I'll call this 2x squared y dy dx. And then I'll tell you what else I'm going to do as well is while I'm at it, I'm going to move the terms that don't have dy dx over to the other side. So I'll keep the dy dx on the left, and then the non-dy dx terms over, we'll move those over to the right. Okay. So I would call this 2xy squared. I'm going to go ahead and move that over. And then 5y, y times 5 is 5y. I'm going to subtract that, move it over. Okay. Move that over to the right side. So I just have, let's see, I have plus 5x dy dx equals negative 2x, that's a terrible 2, negative 2xy squared minus 5y, okay? Then we need to factor out the dy dx. And matter of fact, again, as I'm going along, I'll kind of show you where maybe you could skip a step here or there. I think when you get here, you're just factoring out a dy dx and then dividing by what's left over. So you could certainly do something like this where you say, all right, well, I know what dy dx is going to be. So dy dx is going to equal what I have on the right side over what I have on the left side without the dy dx. Remember, I factor that out to have dy dx. I'd have dy dx times 2x squared y plus 5x. That's what I end up dividing by. Okay? All right. Now, normally we'd be done, but remember, we're looking for the equation of the tangent line. So remember, this is the expression dy dx. That's the notation, actually, remember, for slope of the tangent line. Okay? So we have to plug in, anywhere we see x, we plug in our x coordinate, which is 2. And then anywhere we see our y coordinate, we plug in 1. So it goes like this. It's going to be -2 times 2 times 1 squared minus 5 times, here's a y, 1. Put that all over 2x squared, so 2 squared, times y, 1, plus 5 times 2. Okay? And I'll tell you guys, I'll let you do the math here. In the numerator, you would have got -9. And in the denominator, you should have got 18. So this should simplify to -1/2. So you should have got -1/2 out of this. Okay, if you did that math correctly. So now you remember the equation. We got a point on the line. We've got our slope now. So now let's use point slope, and then we'll eventually arrange it into slope intercept form. So I'll get a new page for that. All right. So it's going to be, like I said, y minus our y coordinate, which is 1, is going to equal our slope. And then it's going to be x minus our x coordinate 2. Okay. So then distribute that -1/2. So it's going to be y minus 1 equals -1/2 x plus 1. And then add 1 to both sides, you get y equals -1/2 x plus 2. So that is now the equation of your tangent line to that curve, to that graph at the point 2, 1. Okay. All right. Like I said, I wanted to do a couple for you guys. This one's going to look not so nice. Okay. Again, let me do a quick pause to get everything set up for you. All right, so let's take a look. So I want to do another one where we found the equation of the tangent line. And if you take a look at number 313, we'll take a look at that. And I've got that one written down already, so let's just go directly to the whiteboard. Okay. So here it is, xy squared plus sine of xy. I'm sorry, not sine of xy. That's not right. It should be sine of pi y. Let's try that again. So this middle term here should be, I guess it's sine of pi y, which is very different from xy. Minus 2x squared equals 10 at the point 2, -3. All right, so we got to go through. Remember, our first step is to find the derivative. So xy squared, there we have a product rule. All right, so again, I'm not going to keep writing the dx part. I think you guys are aware of what's happening there. All right, so xy squared is going to be first times derivative of y squared, which is going to be 2y times dy dx, plus, and then we've got y squared times the derivative of x, which is 1. Okay. Plus, now we get to sine of pi y. This is going to be a chain rule. So first you start with sine, and it's going to be cosine of pi y, times, now you go inside the function to pi y, and remember, pi is a constant, right? So the derivative of pi times y is just pi. But remember, we still got to do the derivative of y, which is a function of x. So we got to do times dy dx. Okay? So all of that for sine of pi y minus, and then how about 2x squared? What's the derivative? That's just 4x. And that's going to be set equal to the derivative of 10, which is 0. Okay? All right. So again, I want to isolate the dy dx terms and then get all the non-dy dx terms over the other side. I'll do that simultaneously as I do simplify each term, basically. All right. So I've got this x times 2y dy dx. I'm going to keep this on the left side and call it 2xy dy dx plus, and then y squared was going to go to the other side. I'll do that in a second. Okay. And then I've got cosine of pi y times dy dx. I'm going to take this pi and put it in front of cosine just to kind of avoid confusion, to make sure it's not within the cosine. So it's pi times cosine of pi y dy dx. I'm going to set that equal to, so then the minus 4x is going to go to the other side as well. So I'm going to take, so again, I'm going to subtract the y squared times 1, that's y squared. We're going to have it over here. And then I would add 4x. So I'm going to have it as 4x minus y squared. Feel free to put negative y squared plus 4x. I'm one of those, I'm weird one. I like to see the lead term be positive if I can help it. But don't feel like you have to do that. So you can have negative y squared plus 4x if you'd like. Okay. So here's where we're at. Okay. So then, again, I'm going to show you, kind of combine two steps into one. Our next step here would be to factor out the dy dx, and then we divide by what's left over. All right. That will give us the derivative. So dy dx is going to equal this 4x minus y squared. All right. And then we put that all over. And remember, we factored out the dy dx from both of these terms. So I'm going to be left with 2xy plus pi cosine of pi y. Okay. All right. So here we go. So now we start plugging in our values. Okay. So everywhere we see x, we're going to plug in a 2. Everywhere we see y, we're going to plug in a negative 3. So I'm going to do 4 times 2 minus, be careful here, it's negative 3 squared. Put that all over 2 times negative 3 plus pi times cosine of pi times y. So it's going to be pi times cosine of, I guess it's going to be negative 3 pi, because it's pi times negative 3. Okay. All right. And let's see. Cosine at negative 3 pi. I think that would be negative 1, I believe. Okay. Let's take a look here. I just want to make sure, again, everything is set up in my notes here. Yep, that'd be negative 1. So what that means for this, and I'll show you, the math is going to be a little weird for this one, especially, and then when we get to our answer. So if you did the math correctly in the numerator, I know I'm skipping some of the math steps here as well. If you did the math correctly in the numerator, this should come out to negative 1, because it's 8 minus 9, okay? So it comes out to negative 1 up top. And then in the denominator, I've got 2 times negative 3. That is negative 12. Okay. And then I have plus pi, and then cosine at negative 3 pi. Cosine at negative 3 pi is negative 1. So this would actually be, and I need to keep this exact, this will actually become minus pi. All right. So to make this look a little bit nicer, I notice that all of my terms are negative, the numerator and the denominator. So if I have a negative 1 up top, if I factor out a negative from the bottom, then the negatives cancel, and actually I can make everything positive. Excuse me. Okay. So I'm going to have 1 over 12 plus pi. That's going to be my slope. I know it's not ideal, but we're going to go with it. Okay. So sometimes that happens. All right. So now we go to our get to our equation of our line. So let's put it into point slope. So it's going to be y minus negative 3. So it's y plus 3 equals our slope, which is 1 over 12 plus pi. And then in parentheses, x minus our x coordinate, which remember was 2. So we were at the point 2, negative 3. Okay. I'm going to distribute that 1 over 12 plus pi. So it's going to be 1 over 12 plus pi, pi times x minus, and then this will be 2 over 12 plus pi. Sorry. I don't know what I was thinking there. 12 plus pi. All right. And then now to get it into official slope-intercept form, I would subtract 3 from both sides. All right. And then I would get something like this. And then from here, I'm going to work with it a little bit. So 1 over 12 plus pi x minus 2 over 12 plus pi. And then what I'm going to do is I'm going to get a common denominator for that 3. Okay. All right. So that way I can combine, just have one kind of written out y-intercept, if that makes sense. All right. So I need to get a denominator of 12 plus pi. So that means I'm going to have up top a 12 plus pi as well. So that's why I'm going to have 36 plus 3 pi. That was the product of 3 times 12 pi. Remember, I have 3, right? And I'm writing 3 as I multiply it by 12 plus pi over 12 plus pi. That's why I get that. All right. Well, I'm going to need a new page to finish this off here. Okay. So now I'm going to write it. I'm going to put another step in here again, just so everybody's understanding of what's happening on this particular, how I'm getting my answer. So I've got y equals, I got 1 over 12 plus pi times x. And then I'm going to have minus 2 over 12 plus pi. And then I'm going to have, see the 36 plus 3 pi? I'm going to separate those into 2 separate fractions. Now remember, I'm subtracting this whole thing. So I have to do minus 36 and then minus 3 pi. I'm subtracting that whole thing. So I'm going to split it up so that it's minus 36 over 12 plus pi. And then it's minus the 3 pi over 12 plus pi. That way I can combine, you see the negative 2 minus 36, so these two fractions we can combine. So it's going to be y equals 1 over 12 plus pi times x. That's my slope, the slope part of the slope intercept. And then I'm going to have minus 38 . There we go. Let's try that again. 38 over 12 plus pi minus 3 pi over 12 plus pi. So then what I'm going to do, again, combine it back, because this part here I want to combine so that it just looks like one y-intercept, even though it looks like the messiest y-intercept ever. So we're going to have y equals 1 over 12 plus pi x. And then because they're both negative, I'm going to have a minus, and then both terms in the numerator become positive because I'm factoring out the negative. So I'm going to do 38 plus 3 pi over 12 plus pi. Okay. So that was a doozy. That pi really throws a monkey wrench into things, doesn't it? All right. Okay. Couple more. Stay tuned. I know I keep pausing the video. I just want to make sure everything is correct and set up properly. So there's another pause. All right. So I got a couple more problems for you. This next one takes a little bit different approach. Still uses implicit differentiation, but just the types of questions that are being asked. So it says for the equation x squared plus 2xy minus 3y squared equals 0. Part A says find the equation of the normal to the tangent line at the point 1, 1. Now, normal means perpendicular. That's math speak for a perpendicular line. And that's going to be important because if you remember what's true about, think about two lines and if they're perpendicular, what's true about those two lines? We'll take a look at that in a second. And then part B says that at what other point does the normal line in part A intersect the graph of the equation? All right. Okay, so let's go. I got this set up again on the whiteboard. We go there. All right. So again, first we're required, we have to find the slope of our line at the point 1, 1. So we're going to take the derivative and we're going to do this implicitly again. Okay. So x squared, we take the derivative of that. Again, I'm just cutting right to it. I'm not going to write the d over dx, but you certainly can if you need to. X squared, the derivative is going to be 2x. 2xy, we need a product rule. So I'm going to do first 2x times the derivative of y, which is 1 times, and I got to multiply that by dy dx, very important. Plus, and then I'm going to have y times the derivative of 2x, which is 2. And then I've got the derivative of minus 3y squared. That's going to be minus 6y times dy dx. And then, of course, on the right side, the derivative of 0 is 0. Okay. So I'm going to keep dy dx on the left side. Let's move non-dy dx terms to the right side. So I'm going to keep the 2x dy dx on the left. And then I'm going to have minus 6y dy dx on the right side. And then on the left side. The dy dx's are on the left side. Now on the right side, I'm going to have the 2x and then the 2y. But remember, I subtracted them to give them over. Okay. So I'm going to have minus 2x minus 2y. Okay. And then again, I'm going to cut right to the answer in terms of like how to express the derivative. We factor a dy dx out of all these terms and then divide by what's left over. And that's going to leave us dy dx equals, we've got negative 2x minus 2y over, and then on the bottom we would have 2x and then minus 6y. Okay, so that's our derivative for any point, any value of xy. Okay, so now specifically at the point 1, 1, we need to find the slope. So we're going to plug in a 1 for x and then a 1 for y. So it's going to be negative 2 times 1 minus 2 times 1. All right, and then we're going to put that over 2 times 1 minus 6 times 1. And if you did this correctly, you would get negative 4 over negative 4, which gives you a positive 1. Okay. Now remember, that's the slope of the tangent line. All right. The slope of the normal or perpendicular line to that, remember what's true about perpendicular lines. Their slopes are what are called opposite reciprocals. Okay. So what that means is if you take one, flip it, so got one, flip it, and you change the sign. I cannot talk today. Flip it, change the sign. So when you flip 1, you still get 1. Change the sign, you get negative 1. So the slope of our line, so the slope of the normal line, equals negative 1. Okay? So slope of the normal line equals negative 1. So now to find the equation of it, again, we'll use point slope. So it's going to be y minus our y coordinate equals slope x minus our x coordinate. Okay? So it's negative 1 times x minus 1. Distribute that negative through because we want to solve for y to get this into slope-intercept form. It's going to be negative x plus 1. And then let's isolate the y by adding 1 to both sides. This is going to give me y equals negative x plus 2. So that's the equation of the normal line, which is perpendicular to our tangent line. Okay? All right. So now let me go back to the question here. Just show you here. So remember, part B is at what other point does the normal line in A intersect the graph of the equation? Okay. Well, we want to make sure, okay. So remember, we've got our original equation here, right? Okay. And we want the y. We know that the y coordinate, when we express it like this, so we know that the normal line has this equation, negative x plus 2. Okay. So we want y to equal this. That's where y and this equation that's where these two lines will intersect, okay? So we actually plug this in for any y that we see in our original equation, okay? And then what we're going to do is we're going to solve it for x, and those are the x value, that we'll get the x values for which these happen, okay? All right, excuse me. So let's go ahead and do that right quick here. And then I'll show you how to handle the y coordinate here as well. Okay, so like I said, we plug in this expression, we'll know what the x is, and then we'll go ahead and figure out what the y coordinate will be. Okay, all right, so let's go ahead and do this. So remember, our equation was x squared, so I'm going to leave any x's alone, plus what was it? 2x, and then I multiply by the equation of that normal line, which was negative x plus 2. And then we're going to do minus negative x plus 2, 3. There's a 3 in front of that, sorry. It was negative 3y squared, so it's times negative 3, negative x plus 2 squared, set it equal to 0, okay? So that's what we're doing, is just replacing y with that equation, okay? So it shows that that line will intersect at different points, okay? So, like I said, we're going to solve for x, and it tells us our x coordinate. So we're going to get x squared plus, let's distribute that. Matter of fact, I'm going to get rid of that plus because that term is going to be negative. Okay. Distribute the 2x, so it's going to be negative 2x squared plus 4x. And then I'm going to do out negative x plus 2 squared. Okay. I think that's going to be x squared minus 4x plus 4, if I'm not mistaken, equals 0. I'm just make sure I got that right. I think. Yeah, FOIL. It's a FOIL problem. So, yeah. Okay. Distribute that 3 through now. I'm going to get x squared minus 2x squared, 4x minus 3x squared, plus 12x minus 12 equals 0. Okay. And then when we combine all the like terms, okay, we're going to get, if we combine all the x squared terms, we should get negative 4x squared. And then if you combine the x terms, you get 16x, that's positive 16x. And then we have a minus 12, set it equal to 0. So then from here, I would suggest factoring if you could, which we can. And just to make it easier for ourselves, I'm going to factor out a common factor of negative 4. And when you do that, you should get x squared minus 4x plus 3. Oh gosh, that is not a 0. That's a parenthesis, sorry, equals 0. All right. So then if I keep factoring, I get negative 4. This factors down into x minus 3. And then x minus 1 is going to equal 0. Okay. All right. So then when you solve this, you set each equation to 0, right? Or each factor to 0. Now the negative 4 equals 0 does not matter. The x minus 3 equals 0. The x minus 1 equals 0. Well, that means we get x equals 3 and then x equals 1. Now, we've already got x equals 1. That was our original point, so we don't need to worry about that one. All right. X equals 3 is our new point. Okay. All right. So to find the y coordinate to that, all right, just take 3 and remember, we know that x equals 3. Well, what does y equal? And that'll tell us the point. It's on this line, but it's also in the equation. Okay. So at x equals 3, y equals, remember, it's negative x plus 2, so negative 3 plus 2 gives you negative 1. So that other point is 3, negative 1. Okay? So our first point was 1, 1. We had that already. Okay? So we didn't need to find that. The one we did need to find was the other point, or points, and that would, excuse me, that would be at 3, negative 1. Okay? One more pause, and then we'll go ahead and finish this with one more example. All right, so the last problem I wanted to do, this is going to be just that kind of real life application thrown in there. So if you look at number 323 here, it says the number of cell phones produced when X dollars is spent on labor and Y dollars is spent on capital invested by a manufacturer can be modeled by the equation as so. It's 60 X to the 3/4, Y to the 1/4 equals 3240. We're going to find dy dx and evaluate at the point 81/16. So it's like finding the slope of the tangent line, basically. All right, but then part B is going to be, all right, what is part A telling us in the context of this problem? All right, so first we need to do the work. Okay, so let's go ahead and take a look at this, and let's just do the derivative. We're going to do it implicitly, and we have a term with x and y being multiplied together. So we got to use product rule. I'm going to have 60x to the 3/4 as my first term, and then y to the 1/4 be my second. So it's going to go first times the derivative of the second. So derivative of y to the 1/4 will be 1/4 y to the negative 3/4 times dy dx, plus the second, which is y to the 1/4, times the derivative of the first. So it's going to be 60, or excuse me. Let me just need to think about this again. No, I'll keep it. It's fine, just because I have a fraction here. I'll keep the 60 there times, and then the 3/4 will come down in front. So it's going to be 3/4. Sorry, I don't know why I confused myself there. So 3/4 x to the negative 1/4, and I don't need a dy dx there, equals, and then the derivative of 3240, just a constant, it's going to be 0. Okay. All right. So then to get dy dx, we would isolate the dy dx. I'm going to do a little simplifying here. Okay. And I've got 60 times 1/4. That's going to be 15 x to the 3/4 y to the negative 3/4 dy dx. And I'm going to go ahead and move this term over. So I'm going to move this one over to the right side. While I'm at it, I'm going to do 60 times 3/4. That should be 45. Okay. So that's going to equal 45 x to the negative 1/4 y to the positive 1/4. Okay, and then of course dy dx is found by dividing by what's in, you just have the 1, we don't have to factor dy dx out. So I'm going to divide by this term on both sides, and that's going to give me 45 x to the negative 1/4 y to the 1/4 over 15 x to the 3/4. That's going to be smaller. There we go. Yep. Y to the negative 3/4. And then I'm going to go ahead and simplify this to make it look easier for ourselves here. So 45 over 15, that's going to give me 3. Keep that on top. And then I have x to the negative 1/4 over x to the 3/4. That would give me x to the negative 1 if I subtracted the exponents, which means I've got x on the bottom. And then I have y to the 1/4 over y to the negative 3/4. So if I did 1/4 minus negative 3/4, I get y to the first, so the y would be on top. So I've got 3y over x. Ooh, hold on. Sorry, I missed a negative. I just realized. Go back up to this step up here. So I forgot when I subtracted and put it over here, I needed to have a negative. So this is going to be negative 45 over 15, negative 3y over x. I hope you're yelling at your computer over that one. Okay. So that's the derivative. Okay. And now what I do is I'm going to plug in my values for y and x that they gave me. So remember they said that when, let me go back to it so you guys can see it. So we're going to plug in 81/16. So when x is 81, so $81 is spent on labor, and 16 is y, which is spent on capital. Go ahead and do that. Okay. So that means dy dx is going to equal -3. Remember, I'm plugging in 16 for y, and then 81 was on the bottom, which was x. When it's all said and done, you should get roughly -0.5926. Okay, all right. I don't know if that's, it might be the exact number, but it might be a decimal representation. Let me just check that right quick. It's 48 divided by 81. Let's see. Yeah, it's a repeating decimal, so we'll call it 5926. Just wanted to double check to be sure. Okay, so remember, that's the slope of the tangent line at the point 8116. So we're done with part A. We found that. So now part B is going to be, let's interpret, what does this number mean? Okay, so this is going to be part B. Here's the interpretation, and I'll type it because I'm sure you're sick of my handwriting by now. All right. So remember, we're spending at this particular point, 81 is X, so we're spending $81 on labor, and then 16 is spent in capital. Okay, so when 81 is spent on labor and 16 is spent on capital. All right, now remember, this is a rate of change, it's a slope. So how does y change for every 1 unit change in x? Okay, so remember, y represents the amount spent on capital. So the amount spent on capital decreases, because we have a negative, right? It decreases by about 59 cents, but I'll put the full decimal in there, or what do we have? At least 59.26. Okay. So the amount spent on capital decreases by $59.26 for every dollar spent on labor. So every dollar you spend on labor in this case, at this very point, for every dollar increase in labor, the amount on capital goes down by about 59 cents. That's what this is saying, okay? So that's the interpretation of what you just found, right? So that'll do it for implicit differentiation. Stay tuned. We'll talk about derivatives of exponential and logarithmic functions in 3.9.